Hi everyone. So I'm part of the lab 19, and here is our results. So first of all, the heat map. We find that there is some difference between some groups in function of the dilutions factor. So the group 1 and the group 3 are very different, but now the group, after 0, minus, and 15. And for the PCOA, so we perform two different PCOA. The first is with the Canberra algorithm. So the difference here is in function of the abundance of the different elements and the different molecules. And for the binary algorithm, it's in function of the presence and absence of the molecules. So we can't just check and see there is a different group. So yes, it can be a quality check, but we can see that these groups are a little different in function of present absence or in function of the abundance of the different elements. So yes, clustering gives different results. And after that, here is the volcano plots, and we just put here some of the molecules that are very significant. So for example, metronol, but also other molecules that we don't write just here, like and I don't remember, but there is, for example, some amino acids and some lipids too. And yes, so we isolated the different clusters and which we were interested. And to finish, a little open question. So we can find the domoic acid in the network, but it's not significant. But for the byproducts, we find different results, because for domoic acid and, for example, the methyl domoic acid, but also for other molecules that I think we can find with the network propagation, there is significant results. So I don't really know what this means, but yes, so that is our first results.
Yeah, so now let's start with the A, right? Or let's continue with A, and that would be lab 1, right?
Yeah.
Okay, awesome. Let's see. And then, yeah, the others, you can just then come up and open yours. I hope you know how to start this in here better than I do. Okay. Here you go.
Hi, everyone. So this is the results from Lab A. First, we try to understand what these samples are. And I guess it's algal bloom. It's when alga expands and it releases toxins, I think. I'm not sure. Yeah. So the different groups that we have is different concentrations of the metabolites. So from the PCA plot, we can see that we have one group that is out like this spot. It's from the 5 concentration, and we can see it also here. And we could also see it in the tree that we did. So it's something that may suggest us maybe for next time to first look at this heat map and maybe exclude this specific sample because, or maybe this specific area. You can see the arrow, yeah. at this specific area because it's really differs from the other samples. So maybe if we will do the analysis again, we will disregard this specific sample. Next, we looked on the volcano plot and looked for the samples that are with the lowest or highest p-value. And we saw this metabolite, the 191, and we went to the GNPS dashboard and we actually saw it's all over the chromatogram. So we decided not to focus on this metabolite. It looks like a noise from the background. So we continued to other metabolites. And there was a metabolite, this one. We saw it in the cluster. It didn't have annotation from the GNPS. So we went to Sirius and it gave us a certain possibility, a certain structure, which is this molecule. We read a little bit about it. It seems like it's a synthetic molecule and not natural one. So we probably, this is probably not a structure from our sample, but it can be something very similar in the structure. We also found this metabolite. It was hard to find any information about it. It has a notation from Peter Dolstein lab in the GNPS, but we read it's something related to silkworm. I'm not sure how it reaches to the algal bloom, but maybe there is a certain connection there. And another interesting metabolite, we saw that Daniel entered it to the GNPS, ergarol. It's herbicide, so maybe it's something that was supposed to inhibit the algal bloom, and it was extracted in the samples. And that's it. Thank you.
Can I ask you one question?
Yeah.
That apparent failed injection you saw, did all of the group members saw that in their data analysis?
Which one?
That,
Yeah,
yeah,
it was in all our data. Yeah.
How to review slideshow? Yes, it's okay. So yeah, I'm the presenter of the group B, well, group 2. So as a first, I just want to have an overview of how we process and our data following the guidelines. So here are the just the overview of all the samples from the lab 2 MS data. So we just have a very brief overlook about all the spectrum, all the peaks and from the spectrum. So some of them, for example, like the black ones, seems kind of different, but you can see many of the samples, they share the same peaks and behaves kind of similarly. Yeah, and then we did something, we played a lot with networks. So here's a kind of we selected randomly a subset of the network just to show how some interesting features. For example, here we can see the different time points. Although they shared chemically, they shared kind of a high similarity, but from the chart, so we can still see the very different patterns. How they accumulated, how they are produced at a different time point of the experiment. You can see some, for example, these two, they have very strong similarity, but you can see they are basically quite dominant at different time points. So then we have the overview of the retention time. We just plot the retention time of the whole network. So we can see some of the groups are kind of a bigger. Well, this one is the one we chose in the previous slide, but we can see some clustering effect. So then we highlighted one of this because it's the purpose of doing that is we try to find a small subset of the network which are kind of well annotated. So here's the one. They don't have too many members from the network, but fortunately, all of them are kind of labeled from the database. So here's an example showing those compounds, and we also dig a little bit about the function of those compounds, and we found that basically related to the secondary metabolites related with the sweeteners, and related with what we ate from licorice, and so that's an interesting group. And then we did some molecular net enhancer. So from the clusters of the compound groups, so we have different groups like that. So yeah. And then we did some statistical analysis. Did some optimization problems, so that we tried to optimize the clusters between 2 and 3. Yeah, here's the example showing the chemical or metabolic profile of all the samples from our batch. It shows kind of similarity between the day 1 or the reference and day 5, which is the red dots. So they are kind of clustered together, so they don't have very strong differences between these two groups, but you can still see quite those day 15, the orange ones, and the day 45 and green ones, they are quite dissimilar. So from the tree, you can also see they clustered quite clearly in 3 different groups. And here they are. So according to the abundance of the metabolites, we plot the heat map. And as you already seen in the previous slide, so the orange one, day 5, and the day 0, or the reference, they are quite close, and it's really hard to tell the difference. And then it's day 15 and day 45, they behave really differently. So if we check the heat map, they have very strongly different patterns. And then we did some, we tried to focus on some the most significant compounds from those data sets. So here's the basic analysis we did from the data set, and we tried to locate the most abundant, actually 25. So the green ones are the most abundant 20. So yeah, because we have different group members, we did process the data slightly differently, and we got slightly different output as well. But we still found a very similar significant compounds, for example, like this one. So actually, we when we move back to the network, we can find that it's something like related with lipid dynamics, I would say. So I don't know more details about the compounds, but it seems that we still have some similarities, and which can be interesting for the further processing or for further analysis. Yeah, that's it. Thanks. Huh? Second.
So we basically did all the same. So I'm not going to go into background or something like that. What we tried to do, try to see in our group how similar our data, and they were pretty similar. Like we did all the PCO plots and heat maps comparison, and they looked quite the same. So they basically took the data set that we processed with Sirius also, and we present data for this one. Yeah, so PCOA plot looks quite similar for all of us. We saw this separation of the group with the highest concentration of algae from the rest, and all of three groups are quite separate, as you can see. And yes, then we did the heat map clustering, and for that data set, we saw that actually it clusters nicely also in the two groups. So the highest concentration of algae groups clustered separately from the rest of three groups. And yes, then we did this beautiful volcano plot, and we saw these masses that are supposed to be the top and supposed to show the most, like they're supposed to be the drivers of this significant sea. I don't know. And yeah, but within these masses, we didn't find any matches, not in Sirius, not in GNPS. And that's why we wanted to see, okay, we have this ANOVA data, and we want to see like what actually from these significant values we can match with the libraries. And we saw like 28 compounds, but 3 of them shows no significance between the control, like no algae and like maximum concentration of algae. And we were like looking at that, see how they actually, the compounds match in the database. So we go through the spectra to see the chemical structure and see how MS data look like for one of the compounds. And also we choose the compounds that shows like the highest p-value score. That was a lipid. We also saw that it's quite nicely matched. Yes, and then we did some nice cytoscape activities with like ANOVA significant annotated features. There were like 2 main clusters and like 1 compound that are like have this loop. And then we saw, okay, what can we get more from the cytoscape? And we actually saw several clusters like lipids, carbohydrates, some of the also methyl-domoic acid also were like significant in our data set. And yeah, and some of the compounds like D-peptides, we also saw them quite a lot clustered together. And yeah, that's all.
Do I do presentation mode or should I download it?
Just click on slideshow on the top.
Right. Oh, okay, thanks. So this is the result of lab 6. We didn't put all of the results, so sorry for that. This is our heat map, and we can see very nicely that if you look at the different time points, so the 0 and the 5 are really close together, and then 15, and then the farthest for them is the 45, which very logically that they're producing different time things over time. We look at the result from the ANOVA, and we looked on the most significant features. We looked for them in the molecular network, and we saw that the three most significant features were in the same clusters, which means this family of molecules is probably being produced by the algae over time, but none of the molecule in the cluster have some identification. So we moved to the next one. It was with the M/Z of 245, and it was a dipeptide. And it's the dipeptide in the middle of the circle. And we thought probably because of the cluster, it could be identified. It also have a nice difference we can see in the box plot between the 0 and the 45 times. And it was really interesting also to see that most of the dipeptide that were recognized here were produced over time, like were more of them over time. So when we tried to understand what this compound is, we went to Sirius, and Sirius was very confident about the formula of it, but there's a lot of red boxes. There's not so sure about the structure, but it seems it's probably will be some dipeptide. That's it.
So I will present you the results from Group E or Laboratory 7. And first we started with showing a bit what is looking at the data or the samples we have and what they are. So as it was already said, it's a simulated algae bloom with different concentrations of standardized algae extracts. And the acquisition was done in different labs, and we take one lab and show you how we got on with the data. So first of all, we wanted to see how our feature finding was in the MZ mine on Tuesday. And we just looked how many features we had. And after the blank removal or the data cleanup we did with EPSAS on 2 days ago, I think it was, we looked how many features were left. And as you can see, for example, here, me and Nika have the same amount of features, and it was for one reason that we used the batch file. And I personally used the batch file because when I tried on my own to select the features, I ended up with not really many features, like 1,500 or something. And it was like, okay, maybe I have to adjust to find more features. And we had the blank to sample ratio of 30%. And then we want to start with some of the PCOA plots. And we just see here again that it's the 45 or after 45 days or 40-50 ppm is most separate on the side. And here you can see the 50 A50M samples, and here the water and the A5M are again clustered pretty close together. And in the next one, you can also see the same pattern, that the 5 and M or reference water are close together, and 45 and 15 are quite far apart. But in the Jacquard distance, where it's more like the binary system, so if something is there or something is absent, you can see that now the 15 and the 45 are closer together, because they share more molecules that are the same. And instead of 5 and the water, which are now further apart, because even if it's in a really low abundance, it's still a difference between not there completely and a bit there. So we also separated the water from the sample with the lowest concentration. Afterwards, you have here the heat map, where you can see again, as we saw today, often that we have 3 clusters, and water and the lowest concentrations are combined in one cluster and the other 2 are separate. And then we also looked at our volcano plot and looked how many features are significant. And as you can see, we got like 1,000 of 4,500 features are significant, and we selected some of the top features to look more into detail. And one of those, which was not annotated but really significant in the uprising, was this feature here, where you can also see that the box plot shows that it rises constantly up to the samples with the highest concentration. And here you can see the molecular network or small molecular network. And for example, here we could also suggest that with the 28, it's C2H4, so an ethyl group that was added. And afterwards, we tried to analyze it with NAP and MolNet enhancer. And this told us that it was an N-acyl alpha amino acid. And the series output, I think it was. Okay, yeah, the series output gave us for the small one this structure, or this structure or the formula, and for the biggest one, this formula, but we think it's not perfect, or it's probably not those formulas, but we have something to start with. And here we went for the other side of the volcano plot, and we had also one of our most abundant features here, as you can see by the size of the node. And here it follows the trend of going down, but this 15 is a bit of an outlier in the box plot and is a bit high. We don't really know why, but still significant. And here you can see again the separation in the different samples and the network. And then, because we saw that there are 2 nodes with the same MZ, we wanted to see if they really are different features, so separate by retention time, or if it's just mistake in the feature finding or anything. And we used the GMPS dashboard to overlay the different chromatograms, and saw that they are separated quite okay or good. So that's a real that are different peaks, or those are different features. And then the NAP and MolNet enhancer again suggested us that this is a cyanogenic glycoside, and Sirius suggested a molecular formula. And with the molecular formulas, or with the molecular formulas suggested by the SMILE codes from Sirius, we loaded them into the cytoscape, but this doesn't really look like an cyanogenic glycoside, but we still have them here and have like a starting point if you want to look deeper into it. And then we have also the domoic acid case, because no one of us found annotated domoic acid in his sample, and we only found the methyl domoic acid form. And the methyl domoic acid has this 326.16, as you can also see in these 2, and up here everywhere, and here's also one more. And we also found domoic acid by its mass, but it was not annotated. So we could find it over the molecular network with the help of our annotated methyl domoic acid. We can also see that you don't need to have your molecule directly annotated if you have, again, like this 14 difference, and then you can start thinking what it is and test it again. And that's it.
Hi, so I will present the results from Lab 8. Here's our heat map. And here again, we can see, as in many groups before, that there is a nice difference between the undiluted samples and then the diluted ones in terms of the features. Then we also did the PCOA comparison, and here you actually see the same plots, but from different people. And the first one is done with a MZ-Mine. The first batch of the first data set was processed in MZ-Mine using the just batch settings. The second one was slightly adjusted, and then the third one had a missing sample. And still, in all of them, you can see that there is a nice separation that is largely explained by the difference in dilutions or time points in the algal bloom. Yes, also our volcano plot. So the features that were significantly different between the groups. We then went into and looked into those ones that were significant and annotated. So we have a huge table. I will just maybe highlight the interesting parts. So we, for example, have a few compounds that are harmful to aquatic life, some plasticizing agents. Interestingly, a lot of compounds that are found in meat or dairy products. And we also looked up that there are actually quite a few farms near this, like near where the samples were taken. So maybe some kind of runoff is happening. And also a few metabolites present in algae and plants. We the domoic acid, and also it was quite a significant difference between the undiluted samples and diluted sample. Yeah, for us it was annotated. Then this is also quite interesting. So we found the network of dipeptides, and 2 were annotated, and we thought that maybe it's possible from there to kind of search through the network and identify the rest, basically. And then this one, the left one is interesting. It's a network of not annotated compounds, but you can see that they're really different in terms of the amount of the compound in the time point. So some are really present in the high concentration, and then some in low concentration. So maybe some kind of, if we mimic algal bloom, some kind of degradation or metabolism is happening. And finally, we talked to a few other groups, and I think, well, maybe not many people found capsaicin, or maybe no one. And we thought that maybe this is something was wrong with the sample processing. So maybe it's it was added like a blank. So something was different in there. Yeah, and I think that's it.
Normally never use. Oh, top right. Okay. Thanks. All right, I'm gonna present the results from lab group 12. So, I mean, we're all familiar with the workflow, so I don't need to talk really about that. So here we first looked at the ANOVA significance between the samples, where the most significant compound here was actually annotated as monoline, if I pronounced that correct. And we also had a look at the significance from another perspective, from the Tukey test between actually the samples. I should have noted on the 0 dilution and the 45. And here you see the principal coordinates plot. Actually, they kind of cluster, but not so nicely, which then leads to the question that we maybe should have then used a different metrics here to display that data a bit better. But you can see nicely that here, can you actually see that? Yeah, you can see when I move my mouse here. Yeah, 15 and 45 actually cluster more together than 10.0 and 5. Then we had a look at the heat map here with also like a lot of other groups, these three different clusters with for time points. You can see that, yeah, 0 and 5 cluster more together, and there's a bit more difference between samples from 15 and 45. And also you can see nicely in the heat map how these clusters actually differ from each other. And then with the MolNet enhancer, we had a look, and Cytoscape, we had a look at the different superclasses here that were displayed, and we had a specific interest. We thought we're going to pick out this mono lane that we found as highly significant, and had a look at that, at the mono LED cluster that we found through Cytoscape and the analysis. You can actually see nicely here at the mono lane that was annotated that it's yeah, mainly in the higher time points like 45 or 15. And yeah, then we also checked for that compound further on with the XIC plot. You can also see nicely that the ones for 5 versus 45 versus 0 time points, you can see it in the high intensity at 45 time point, then at 0, which is also then displayed in another way at the bottom graph. Yeah, and that was it.
Yes, so I'm going to present the results for lab 16. We kind of expected to have some differences in our PCOA plots, but it all looked quite messy for all of us. And the p-value is very off. On the heat maps, it looked a lot better actually after we removed all the zeros. This is where we will remove the zeros. And then for the univariate analysis, we only saw 2 features that was significant different. We tried to run them on series like an hour ago, but the server didn't have any space, so we couldn't perform any fingerprinting or something of those. And then we tried a GNPS dashboard analysis. We saw for one of those masses, and we see a difference in the box plots, but you can also see that we might have some time shift in the retention times. And then moving even more backward to the MSET mine, and when we zoomed into a time interval, we can see that there doesn't seem to be or the chromatogram isn't that very well aligned. So also the Cytoscape files looked very messy. So the conclusion is that with a better LC, it might have been a little bit better. But what we can do with this data is to maybe optimize the parameters a little bit more on the MSET mine, maybe set the threshold a little, change the threshold a little bit, because all of us got over 10,000 features. So it was, yeah, like that. That's it.
That's actually a really interesting example. And unfortunately, you may see such a thing like more often as you like proceed. So who of you has a suggestion on how to fix that on the enzyme? So at what step in enzyme would you do that? Where? No. Where? No.
Noise level.
No. So there's one module at the very end where like the retention times really will bite, the retention time differences will really bite you, right? And this is when you try to bring them all together in the alignment set. So if you notice a retention time shift between some samples, right? I mean, best is to actually rerun it with like some, I don't know, like system or like this system pattern shape. But if you cannot do that, or if they're not like too traumatic, I would increase like the tolerance for like the retention time in the alignment. And then hopefully like those peaks that are shifted will still be like matched together. And there's also like an alternative module, the ransack aligner. So they kind of like work a little bit with like global shifts there, right? So like you can like fix that in MC9. So now it's actually awesome that you mentioned like also the problems with the data set. And then obviously, you know, that would explain why there was like not such strong clustering in PCOA space. So thanks.
So I'm representing the lucky Lab 15, but I promise we did something on our own. So here you can see our heat map. And what we found is that the groups of time point 0 and 5 are almost the same. So they are quite similar. And the most diverse one is group 45. And we can also see that here that 0 and 5 are here down at the bottom together. 15 is over here and 45 is in there. So then we wanted to show you the volcano plots of 2 of us, because we found that a lot of hits are really differently annotated or found. And we then had a look at all of these ones, which we both found, and tried to see what they are. So for example, we found in our cytoscape network, we found this hit here, which is like nicotinic acid alkaloid. And we also found that it's most abundant in group 45. And all the other things which we saw here are mostly fatty acids. And it was the same for the other analysis too. And we found one hit like this one here, which had a match to a database with stearidonic acid. And we found in literature that this is a known antimicrobial compound produced by algae. So this is what we spend our time on.
So now lab 22. Lab 22 loves metabolomics too. We had some interesting problems very early on, but let's first think what the whole goal of this was. Several labs decided to see what the influence would be of the different lab studies, and I think our lab is an example of that. Actually makes quite a bit of difference. We saw some others as well. You start with a sample prep where everything is the same. So you mix some random standard mix some powders you found in the club, and then some algae cell lysates of different concentrations. And then send it out, and all different labs do different LCMS analyses.
I think mostly had C18 with Orbitrap, but I'm not completely certain. And then you let the analysis, you do the analysis by newbies. That was us, and we probably screwed up, but we still got something. And because our lab was probably one of the labs who had the least features already early on, we tweaked some parameters in MZ-Mine. All of us did, and you can see this had quite a bit of effect. I think Marlene had probably changed least. I was not too big a change, and Ian actually changed quite a bit on the settings in Panya, and that shows in our following analysis, which I thought was kind of interesting. So the PCOAs, we just as almost everyone saw that it really makes a bit of a difference which algorithm or distance matrix you choose. I always think it's a bit like p hacking, although it's not completely p hacking if you then find a clear pattern. But the clear pattern in general for our lab at least was that 45 was the outlier in everything, and the others were a bit more similar. And this showed as well, as soon as you do the heat map, again, it showed it made quite a big difference if you do a Manhattan or a Canberra. And actually, Manhattan is sort of what we expected to see, but most of the matrices or methods actually showed what Canberra. So in that case, it's the blank, the M, and the A5 and A15 are grouping together continuously. So then we did, and this is an example of mine, but we all saw something similar. Some had some more significant features, some less, as you saw at the first or second slide. And this is one significant compound, dibutylphenylalanine. I found that I couldn't find much about this compound. So I'm not sure what we were going to say about this. So I'll leave that, and I'll just leave it Lab 22 lost metabolomics 2. But probably wasn't too good at it.
So how maybe we make it? Oh yeah, perfect. Okay, so we forget to put our numbers. So we are lab 18. Yeah, and just to make it like short, I think also the separation in our PC was like quite as expected, and so this actually is the binary separation. And also for the heat map, there was nothing like it was quite similar to all of the other groups. There was a nice separation between the time points. Yeah, so maybe the most important, interesting thing we could find is that we had kind of this group here, but I think many groups didn't have. So we actually tried to figure out what they are like with Sirius, but we couldn't find IDs or something to identify. But I think when one would reiterate on this sample set, this will be the most interesting features to start with. I mean, it's the downregulated one, so maybe it's the metabolites that are catalyzed by the catabolized by the algae. So yeah. And finally, yeah, so this is like just one node setup we tried. So what you see here is we put the size of the nodes, actually the fold change. The color represents the significance of significant features. So I mean, yellow means like a really, really low p-value. So maybe we thought we could also show it in this way in the node setup. Like kind of resembles a volcano plot. Yeah, and here within those highly regulated things or highly different things, the most important time point is time point 15. So maybe that's a change that like started to happen and then also was removed after there was the 45 time point. Yeah. So this was our summary. Yeah.
Guess that was all. It's pretty amazing to see what you got out of it. And yeah, I don't know, like at the end, I hope this kind of like leaves you with like the, you know, like confidence that, well, all of the groups got some results, like you used the different tools, which I think makes us quite happy, because that means that what we taught you over the week kind of like was at least like a little bit received. And it also makes us quite, I guess, happy to see that a lot of the results are kind of like, at least from a global perspective, are kind of matching. So now there's like tiny differences, of course, but that's expected between the labs. And some of like the bigger differences also already had an explanation, such as like retention time shifts. That's of course something we probably gonna now look into detail. But yeah, I think overall it has been a pretty fun week with all of you, a very intense week. So I guess we're all tired and gonna go home and sleep hopefully soon. But yeah, it was super fun. And obviously this was a big group effort. So many of the speakers are already on their way home, but of course it would have not been possible without them. And it would have not been possible without like all of like the local people here, many from my lab, but also from other labs here in the CMFI cluster that, you know, like prepared the coffee, cut it like the bread and pastries, and yeah, like kind of like organized all around so that we had like a fun summer school. So I just want to give a huge applause to all of them. And yeah, I want to say a super big thank you. So yeah, thanks a lot for doing this and for, you know, making this a fun event. And then yeah, last but not least, I want to thank all of you for coming and for being such like an awesome group of people. It's been super fun, and yeah, it's been pretty amazing to see what you got all out of it. I hope you will continue using the tools, maybe in a different way. Maybe you find out that some, you know, other combinations might work out better for you. Then please also let us know. Maybe we can learn from you what we could do better. And yeah, I hope to see some of you or all of you in the future at conferences, maybe at VMall or at the summer school next year that hopefully Madeleine and her team will host in Copenhagen. So yeah, thanks again, and looking forward to I don't know, interact with all of you in the future.